Hi, I'm Emma.
And I'm Vivian, and today we're going to be talking about Snoopy surpassing the scalability bottleneck of Oblivious storage. This is joint work with Ioannis, Natacha, and Raluca at UC Berkeley and UC Santa Cruz. So end-to-end encryption provides confidentiality, which means that we store encrypted records inside an untrusted server, and even though we store these records in an untrusted server, the attacker can't see the contents of these patient records.
However, access patterns can still reveal private data. And by access patterns, we mean how the user accesses the data. So to make this a bit more concrete, I'm going to walk through a simple example with a medical disease store. So let's say there's some public information about how frequently different objects are being accessed. So let's say the COVID object is being accessed about 70% of the time, the flu object about 20% of the time, and the asthma object about 10% of the time. So over time, the attacker is going to watch the doctor interact with the medical disease store, and they're going to see how frequently different objects are being accessed. And from that, it can infer that the object that's being accessed about 70% of the time is probably the COVID object. So then some unfortunate patient Charlie arrives at the doctor's office. The doctor requests object 1. The attacker can see that object 1 is being requested by the doctor, and then the attacker can infer that Charlie has COVID. So even though the contents of the objects remain encrypted, the attacker can still learn private information.
So in order to defend against these access pattern attacks, there's this rich body of literature in Oblivious storage, or ORAM. And now the doctor, when looking up COVID, will run an Oblivious storage protocol with the Oblivious disease store. And the security guarantees of Oblivious storage mean that the attacker can't learn any additional information. Now, there's a popular setup that we've seen in Oblivious storage in which we run a hardware enclave inside the untrusted cloud and it's co-located with this untrusted storage. Now, the setup supports multiple users as they can all go through the hardware enclave, and it reduces network interaction. For simplicity here, we assume that the clients trust each other, but the attacker can see that the hacker can see network communication patterns and memory access patterns inside the enclave, but not the contents of the enclave. And this means we have to be quite careful about how we design algorithms that run inside the hardware enclave because we don't want the memory access patterns to have any leakage that the attacker can now infer information from.
So this sounds great, Vivian, but existing Oblivious storage systems all have scalability bottlenecks. And by scalability bottleneck, I mean that there's a component where coordination is required for every request, and that component can't be securely distributed. Many existing ORAM protocols are tree-based and hide the location of objects in a tree. And this leads to two common bottlenecks. So the first is location metadata, so the mapping of logical locations to physical locations in the tree. And the second is the root of the tree itself. So all these requests are going to pass through different paths through the root of the tree. And this leads the root to be a central point of coordination, a point where all the requests are serialized. And this is in contrast to a plain text storage system, where objects can simply be sharded across different partitions, and the clients can access the partitions directly without needing any coordination.
Well then, Emma, how do we build an Oblivious object store that handles high throughput by scaling like a plain text object store?
Well, Vivian, I am so glad you asked. So in this talk, we'll be talking about scalable nodes for Oblivious Object Repository, or Snoopy. So Snoopy is an Oblivious object store that scales like plain text storage. Snoopy uses hardware enclaves, and with 6 hardware enclaves, Snoopy can achieve a throughput of 26,000 operations per second. And as we add more enclaves, we're able to increase the throughput of the system. And this is in contrast to prior work like Oblivious that can't scale beyond 2 machines, or Oblix, which can't scale beyond a single hardware enclave.
So now throughout this talk, we're going to first go through the design idea, and then we're going to break down the components of Snoopy, which are the load balancer and the sub-ORAM, and then we'll finish off by talking about Snoopy's performance. So first we'll visit the design idea. So like Emma just said, if we're going to build this scalable system where we want to scale like plain text storage, then we should just look at the techniques in that space that seem to work for them in the high throughput regime and transplant them over to us. So we can partition our Oblivious store into multiple sub-ORAMs in which we shard data across each machine. And then we can have a load balancer in the middle that collects requests from the clients and then assembles batches to send to each sub-ORAM. Now we just run both of these components inside a hardware enclave and we should be secure and scalable, right?
Well, not so fast, Vivian. So this is actually naively insecure. because the batches sent to sub-ORAMs will reveal information about the underlying request distribution. So for example, if a bunch of clients request the COVID object and no one requests the asthma object, the batch sent to the partition containing the COVID object will be much larger than the batch sent to the partition containing the asthma object. And this is going to reveal information about the underlying request distribution. So we have two key goals. So the first is security, so we want to hide the access patterns. If we're using batching, this means that the batch size should only depend on public information that's known to the attacker. The second requirement is scalability. So if we add load balancers or sub-ORAMs to the system, we should be able to increase the overall system throughput. So in Snoopy, we contribute techniques that enable batching and partitioning with security and scalability.
So let's talk about how we'll actually make this load balancer meet our design goals. Well, like Emma just gave in that example before, we have to first handle skewed workloads. So if every client requests the COVID object, then our load balancer is going to receive, say, n requests, and it's going to have to send n requests to every sub-ORAM in order to prevent leaking any information. Now, this doesn't seem very scalable, and it seems like you're better off just running a singular sub-ORAM that just receives all the requests to begin with.
So that's a great point, Vivian. So to address that, we use deduplication. And the idea is that if we have a bunch of requests to the same object, so for example, the COVID object, the load balancer can replace that with one single request to the sub-ORAM containing the COVID object. So for example, if we have a bunch of write requests, the sub-ORAM can replace those write requests with just the last write to that COVID object. And this means that we now only need to handle batches of distinct requests. And here now we can hope to maybe get batches that are smaller than the number of total requests in the system, because we just have batches of distinct requests.
Great, so now that we have these batches of distinct requests at the load balancer, we just need to figure out how we securely set the batch size B, which is the size of the batches that we send to each sub-ORAM.
Exactly. So we have two important requirements for how we set this batch size. So the first is that it should be computable with public information. So this can include the number of total requests in the system, the number of load balancers, and the number of sub-ORAMs. Importantly, this can't include the number of distinct requests because we don't want to leak information about which requests were deduplicated because that can leak information about the underlying request distribution. The second requirement is that the probability of overflow should be negligible in our security parameter. And this is important because we don't want a batch to overflow because that means then the client would have to retry the request. And retrying the request leaks information to the attacker, which can reveal information about the underlying request distribution. So we really don't want this overflow event to happen. So to solve this problem, we observed that in the high throughput setting, there are many concurrent requests. And because we performed deduplication, after deduplication, the requests are spread across the ORAM somewhat evenly because we're just dealing with distinct requests. And so now we actually don't need to add that many dummy requests in order to have a secure batch size. So you might think that we need to add dummy requests in order to have batches that are the size of the number of requests in the system, but actually because these requests are spread across the sub-ORAM somewhat equally, because they're all distinct, we actually don't need to add that many dummies in order to have secure batch sizes.
So this actually looks a lot like a balls into bins problem, and we contribute a bound that meets both of the requirements that Emma just went over and provides scalability because we target the high throughput regime. Our bound also gives you quite efficient performance when we have many requests. So now that we've gone over the batch structure of the load balancer, we're going to dive into the Oblivious algorithms that we use to actually assemble these batches at the load balancer.
So recall from our system setup that we're dealing with hardware enclaves, and this means that the attacker can view not only network communication patterns, but also the memory access patterns. So the attacker can't view the enclave contents, but it can see how the algorithms, which parts of memory the algorithms are touching. And so it's really important that the memory access patterns should not leak information about the underlying requests. So from watching the access patterns, the attacker shouldn't learn private information. So we need to build Oblivious algorithms to create these batches. So we use two key Oblivious building blocks for doing this. So the first is Oblivious sort, which is just going to sort the elements of some array. But critically, it's going to perform comparison swaps in a fixed predefined order so that the memory access patterns don't reveal anything about the contents of the array being sorted. The second primitive that we use is Oblivious compaction. So the idea in oblivious compaction is that we're going to mark different elements of the array for whether or not we want to keep them. And then we're going to compact the array so that we order in the front all the elements that we want to keep, and at the end all the elements that we don't want to keep. And we're going to preserve the order of the elements that aren't within each region. So using these two oblivious building blocks, we can then construct these batches obliviously.
So in order to construct these batches obliviously, we first receive requests from the clients, and then we have to assign a sub-ORAM to each request. And we do this by hashing the object ID that appears in each request. And then we have to add dummy requests. So using our bound from that we just discussed earlier, for S sub-ORAMs in a batch size B, we will add S times B dummies, or basically B dummy requests for every sub-ORAM. Now we have to obliviously sort our requests so that we can get batches. And these batches are going to have different sizes. So we have to obliviously compact out the extra dummy requests and the duplicate requests. Now in order to do this, we make a linear scan over our requests, and we discard the requests that are duplicates or our extra dummy requests. And we use oblivious compaction, and we end up with two batches of equal size with the same number of requests that we can send off to each sub-ORAM. And notice how in all the steps I've described, we either make a linear scan through all of the requests, or we use an oblivious building block that Emma just described. And that basically gives us an algorithm that we can run on the enclave because it's oblivious, and the memory accesses it makes are already predetermined and don't really depend on the contents of the requests themselves.
So Vivian just showed an algorithm for obliviously constructing these batches, but we also need to make sure that we're mapping sub-ORAM responses to the original client requests. We don't have time to walk through the details of this now, and you can see the paper for details, but this is going to use a lot of the same techniques as the algorithm that we just showed. And so some of the key insights, some of the things that we need to make sure that we take care of in this algorithm are that we need to filter out the dummies. So recall that we added a bunch of these dummies to our batches in order to make sure that each batch has the same size. It only depends on public information. So now we need to filter out these dummies. And we also now need to propagate sub-ORAM responses to potentially many client requests. So when we did this deduplication, many client requests could map to a single sub-ORAM response, and now we need to make sure that we propagate the value that we get back to all the requests that originally requested this object to make sure that we're doing the operation correctly with deduplication.
Great, so that finishes off the oblivious algorithms of the load balancer, and now we're going to talk about how we design the sub-ORAM in Snoopy. So traditional ORAMs in the literature prioritize latency and communication for individual requests in the client-server model. And this means that they usually end up using trees or hierarchical structures that support logarithmic access times. And making these client-side ORAM algorithms oblivious adds quite a bit of overhead, and it's also not quite the right fit for our setting since Snoopy is targeting the high throughput regime.
So we instead prioritize throughput for batches of distinct requests in the hardware enclave setting. And this means that we don't really need the logarithmic access times that prior work really prioritized. And so we're free to come up with an entirely different solution. And we're inspired by Signal's private contact discovery protocol. So in Signal's private contact discovery protocol, the goal is, so a user has a set of contacts and they want to see which of their contacts are using Signal. One thing you could do is you could send the contacts directly to Signal. They could tell you which ones are using Signal, but this would be bad for privacy, so they instead use a hardware enclave. And the idea is that they're going to run an oblivious algorithm inside the hardware enclave to tell you which of the contacts that you have overlap with the contacts using Signal. So they do this using what we call an oblivious hash table. So it's going to take as input the user's N contacts and going to create from those an oblivious hash table. So now the hardware enclave can scan through all of the contacts using Signal, and for each user, perform a lookup in the oblivious hash table. So creating the oblivious hash table is expensive, so it's quadratic in the number of the user's contacts. But now performing a lookup in the oblivious hash table is really fast, so it's just constant time. So this is good if the user has a fairly small number of contacts and there are many Signal users in the world. So the expensive part only depends on the number of contacts that the user has, not the number of total Signal contacts. And so this maps pretty well to our setting, so we can just replace contacts with requests. And this is only possible because we perform deduplication of the load balancer, so we're just handling batches of distinct requests. However, this has two problems in our setting. So the first has to do with performance. So oblivious hash table construction is pretty slow if you have many requests. So Signal is really targeting the case where users don't have that many contacts. But recall that we wanted to set our batches to be pretty large when we're creating them with the load balancer in order to minimize the number of dummies that we're adding. So now we maybe have a larger number of requests that we're trying to use to create this oblivious hash table, and so this quadratic factor can be substantially larger and slower in practice. Also for security, Signal doesn't size these buckets in order to prevent overflow with a negligible probability in the security parameter. And this is problematic for proving security formally.
Well, to solve this security issue, we could just maybe dynamically size our hash buckets.
So the problem with this is actually insecure because an object is more likely to be requested if it hashes to a bigger bucket. So when the enclave is performing this linear scan over the entire array, if the object that it's scanning hashes to a bigger bucket, it knows that the probability that object was requested is higher than that of an object that hashes to a smaller bucket. So this is insecure.
Well, then I guess we just need a bucket size such that the probability of overflow is negligible, so we set it in the beginning and then we forget it. It's fine.
So that sounds a lot like what we already did in the load balancer. So remember, we had to set these batches such that the probability of overflow is negligible in our security parameter. Is this the same thing, Vivian?
So I guess we can just use that bound that we have at the load balancer and take it over to the sub-ORAM.
So while that's secure, it's actually not very efficient in our setting because the load balancer bound is optimized for larger batch sizes. So remember that we want to actually set these batch sizes to be really large to minimize the number of dummies that we're adding. In this case, we actually want smaller bucket sizes because performing an access in this oblivious hash table means that we have to scan through the contents of the entire bucket. So if these buckets get really big, the scan is pretty slow, so this constant time for lookup is actually not very fast. So it seems like we actually need something different, Vivian.
So we actually identify an oblivious two-tier hash table to be a very good fit for our sub-ORAM setting, because here in this scheme we overflow requests into a second hash table, and that lets us have smaller buckets so that when we scan the entire bucket, we're actually not scanning too many objects at one time.
So putting it all together, so we take in these n-distinct requests from the load balancer, and we use those to create a two-tier oblivious hash table. And the time to create this table is now O of n log n in comparison to the O of n squared from Signal's private contact discovery. So now we're going to scan through all the stored objects, and for each object we're going to perform a lookup in the two-tier oblivious hash table. If there's a write, we're going to update the stored object, and if it's a read, we'll update the hash table entry. And we can hide whether it's a read or a write using oblivious comparand sets. At the end of this, we'll just send the two-tier oblivious hash table back to the load balancer.
Great. So that concludes our oblivious algorithms for the load balancer and the sub-ORAM design and the oblivious algorithms that we used to actually make the sub-ORAM.
And there's also some contributions that we didn't have time to talk about today, including our balls into bins analysis. You can see the paper for that, as well as our planner design. So we contribute a planner that takes as input performance requirements and output the system configuration. So given certain latency and throughput requirements, it tells you how many sub-ORAMs and load balancers to configure your system with. And we also prove security and linearizability of the system in the full version of our paper.
So now we're going to talk about the performance of Snoopy. So we evaluate Snoopy on 18 Azure confidential compute instances that have Intel SGX. And we compare Snoopy to Obliviously, which runs 2 machines, and Oblix, which runs a single hardware enclave. So our baseline Oblix reaches an average request throughput of 1,200 requests per second, and Obliviously can process 6,700 requests per second. Now Snoopy, when we scale out to 18 machines, can reach a throughput of 130,000 requests per second with an average latency of 1,000 milliseconds. These blue boxes show when we add new load balancers instead of sub-ORAMs as we increase the number of machines in our system. And these are the throughput curves for different average latencies.
So in conclusion, Snoopy is an oblivious object store that scales like plaintext storage. So we don't need to choose between high throughput and obliviousness.
You can find our code and our artifact evaluation at the link below. Thank you.